Every advanced chip ever shipped was inspected by a machine from one American company. They do not sell the lithography tools that ASML sells. They do not sell the deposition or etch tools that Applied Materials and Lam Research sell. They do not sell the silicon, and they do not sell the design software. They sell the eyes, the cameras and the electron beams, and the algorithms that decide whether a wafer is good enough to ship. The company is KLA Corporation. Roughly half of the entire process control market for advanced semiconductor manufacturing runs through their tools. No fab on Earth can ramp a new node without them, and the moat has almost nothing to do with hardware. KLA Corporation was founded in 1975 in Milpitas, California, as KLA Instruments. In 1997, it merged with Tencor to become KLA Tencor. In 2019, the name was simplified back to KLA. Across that 50-year history, the company has stayed pointed at one specific layer of the semiconductor manufacturing stack: process control. That layer answers a single hard question for every fab manager. Out of the billions of features printed on a wafer in the last 24 hours, which ones are wrong and why? Today, KLA has roughly 50% share of the global process control equipment market, which is itself about $10 billion per year and growing faster than the broader semiconductor capital equipment industry. Revenue in fiscal year 2024 was around $9.8 billion. Operating margin sits in the high 30s, occasionally into the low 40s, among the highest in any capital equipment business on Earth. Customer concentration is intense. TSMC alone is roughly 25 to 30% of revenue in many quarters. Samsung, Intel, Micron, SK Hynix, and Global Foundries account for most of the rest. Over the next 10 minutes, we will look at four things. First, what KLA actually sells, beyond the marketing label of process control. Second, why no advanced fab on Earth can ramp a new node without them. Third, the part that is almost invisible from the outside but is the real moat, the data flywheel. And fourth, why every competitor, including ASML, has tried and failed to break the monopoly at the leading edge. What KLA sells breaks down into four main categories, each its own multi-billion-dollar product line. The first is patterned wafer inspection, large floor-standing optical and ultraviolet inspection systems, several $1 million each, that scan a finished wafer surface looking for any deviation from the expected pattern. Tools like the SurfScan, the K-Series, and the new Voyager use light at progressively shorter wavelengths to catch progressively smaller defects. The second category is electron beam inspection, slower than optical but able to resolve individual atomic scale defects at advanced nodes. The third category is reticle and photomask inspection. KLA holds roughly 85% share at the high end here, because a defective mask costs the fab tens of millions of dollars and gets replicated onto every wafer it prints. The fourth category is metrology, critical dimension measurement, overlay measurement, film thickness, surface roughness. Metrology is the only category where KLA does not lead at every node. Hitachi High-Tech holds the top spot in critical dimension SEM, and a small Japanese company called Lasertec holds essentially 100% share of EUV mask blank inspection. But across the full process control budget of an advanced fab, KLA tools account for somewhere between 40 and 60% of total inspection and metrology spending, depending on the node and the customer. Every one of these tools costs between $2 and $20 million. A leading-edge fab will have hundreds of them, scattered across the line, running 24/7, generating petabytes of inspection data per month. None of it is optional. None of it has a meaningful second source at the most demanding specifications. Now to the question of why no fab can run without them. The economics of advanced node manufacturing rest on yield. A modern leading-edge wafer can carry hundreds of dies, each worth somewhere between a few hundred and a few $1,000s by the time it ships. A single percentage point of yield improvement at 3 nanometer is worth more than $100 million per year at a single fab. A single percentage point lost is $100 million destroyed. Process control is the only way the fab even knows where the yield is being lost. Without inspection and metrology, the fab does not know which step is contributing how much to defect density, which tool is drifting out of specification, which reticle is generating bad prints, which wafer needs to be reworked, and which lot needs to be scrapped. At an advanced node, a ramp from first silicon to high-volume manufacturing involves running tens of thousands of wafers through hundreds of process steps, with KLA inspection at almost every step. Every defect that gets detected during ramp becomes a data point that feeds back into the next process tuning cycle. Every defect that gets missed becomes a yield loss that nobody can explain. The fabs that ramp the fastest are universally the fabs with the densest, most modern KLA inspection coverage. TSMC's N3 ramp speed advantage over Samsung's 3nm process is not entirely about KLA, but it is not unrelated. The faster you can find a defect, the faster you can fix it, the faster the node ramps to full yield, the faster the customer gets product, and the faster everyone gets paid. Here is the part that is almost invisible from the outside and is the actual moat. KLA's competitive advantage is no longer the optics, the lasers, or the electron columns. Those can be reverse engineered. The advantage is 50 years of accumulated defect data. Every wafer that has ever been inspected by a KLA tool generated a defect fingerprint, a high-resolution image plus a chemistry signature plus a process history. KLA correlates that fingerprint against the actual yield outcome from the same wafer once it finished the line. Do that for 50 years and tens of millions of wafers across every major fab on Earth, and you build a defect classification library no competitor can match. A new inspection tool from a competitor might detect the same defect geometrically, but it does not know whether that defect kills the die. KLA does. That difference, between detecting a defect and knowing which defects kill yield, is the entire ballgame. It is also why KLA tools come bundled with proprietary software, why customer engineering teams are deeply embedded with KLA, and why the company invests roughly 15% of revenue back into R&D every year. The flywheel runs in one direction. More installed tools generate more defect data. More defect data improves the classification library. A better classification library makes the next generation tool more valuable. Customers buy more of the next generation tool. The cycle repeats. 50 years in, no competitor has the data. No competitor can buy the data. And no competitor can generate the data without first selling tools that customers will buy, which they cannot do because the data does not exist yet. The competitive landscape is worth understanding because it explains why the monopoly is structurally stable. Applied Materials has a process diagnostics and control business that competes in some inspection segments. Large company, large R&D budget, but a distant second place at the leading edge. ASML acquired Hermes Microvision in 2016, betting that combining lithography intelligence with electron beam inspection would crack KLA's E-beam segment. 7 years later, ASML's inspection business is real but still a fraction of KLA's. On to innovation, formed from the merger of Rudolph Technologies and Nanometrics in 2020, has solid positions in metrology and packaging inspection, but does not compete with KLA at the most advanced wafer inspection. Hitachi High-Tech remains the leader in critical dimension SEM, and Nova Measuring Instruments holds a respected niche in film thickness. And then there is Lasertec, a small Japanese company headquartered in Yokohama with fewer than 2,000 employees. Lasertec has essentially 100% share of EUV mask blank inspection, the actinic patterned mask inspection systems that ASML's customers absolutely require. That sub-monopoly inside the monopoly is one of the strangest stories in the entire industry. It exists because nobody else built the tool when EUV was a research project, and now nobody can catch up. Lasertec is a separate episode of this series someday. What matters here is the overall pattern. The process control market has a 50-year incumbent with the most data, a couple of credible second-place players in specific segments, and a small Japanese company holding the EUV mask piece. There is no path for a new entrant to dislodge the structure. Here is the verdict. This is the first episode of the series with a single company protagonist, so the two layers describe one company and its moat rather than two companies. Layer 1, KLA itself. Roughly 50% share of the global process control market. Revenue near $10 billion. Operating margin in the high 30s. customer concentration that would terrify any other capital equipment business. But TSMC, Samsung, Intel, Micron, and SK Hynix collectively cannot move volume to anyone else because nobody else can do the job at the leading edge. KLA does not need to grow its share. The semiconductor market grows for them. Layer 2, the data flywheel. 50 years of correlated defect fingerprints across every major fab on Earth. That data is not on a server somewhere that a competitor can copy. It is woven into the classification algorithms, the customer engineering relationships, the proprietary process recipes inside customer fabs that have been jointly tuned with KLA over decades. The data moat is the kind of competitive advantage you can describe in a single sentence, but cannot reproduce in less than 30 years. 3 risks worth tracking. 1. Onto innovation and ASML closing the gap in specific inspection segments. Both companies have made real progress, and both will continue to take incremental share at the margins, particularly at the lower end of the process control budget. 2. Customer concentration. If TSMC's CapEx pauses, KLA's quarter collapses. The flip side is that when TSMC's CapEx grows, KLA grows even faster. 3. China's domestic process control ecosystem. SME, ACM Research, and several smaller Chinese inspection makers are building out for the domestic market. They are not threatening KLA at the leading edge anytime soon. The pattern is the same as every other episode of this series. Decades of customer lock-in, a structural moat that the AI build-out tightens instead of weakening, and a company whose name almost nobody outside the supply chain has heard. This was episode 4 of Forgotten Monopolies, the companies that almost nobody outside the supply chain talks about, but that decide what the industry can actually build. Next episode goes back into Japan, into a very specific corner of the back-end process that almost nobody thinks about, cutting wafers into chips and grinding them thin enough to stack. The dicing saws and the wafer grinders that every advanced packaging line in the world relies on come from 2 companies. Disco Corporation and Tokyo Seimitsu. Combined market share in advanced packaging dicing, over 90%. If this episode taught you something nobody else is talking about, subscribe for the actual semiconductor industry view of the AI race. See you in the next one.